What's going on, guys? Today we're going to be calculating the pressure of neon gas in a 3-litre container at 122 Kelvin. Now, we're going to be using the ideal gas equation, which is as follows. Now, we want to find pressure. So you have to make that the subject. We know the number of moles, which would be 255 grams of neon equates to 12.64 moles gas. That's lovely. So 12.64, plug that in, times by the constant R, in this case would be 0.0821, multiplied by Kelvin, which is 122, all divided by 3, which is the volume. Your pressure should work out to equal 42.2 atmospheres. Now, that is the equation using the ideal gas law, or ideal gas equation, I should say. Now, you can also do this equation using the Van der Waals equation, which is a bit more tricky and a bit more complicated. However, it is more accurate. And the equation for that Van der Waals equation is nRT divided by V minus NV minus A N over V all squared. I need to get a new pen because this one's starting to get a bit kaput. Might change the red to stick to blue, this would be nice. Now the pressure, ooh, stick to blue, lovely. The pressure would be 12.64 times by 0.0821, same constant, that's not going to change. Same temperature, same system, so using a slightly different equation. The volume would be 3 minus 12.64, number of moles, times by B. Thankfully, we know what A and B were. We've given it. Now A is 0.205 and B is 1.67 times 10 to the minus 2. So you can put that in here. Minus 0.205 multiplied by 12.64, 3 all squared. The pressure should work out to equal, you can do this yourself as well with the calculator. The pressure would work out to be 41.75 atmospheres. Now, using the ideal gas law and the Van der Waals, I see the W, we get 42.2 here and 41.75 atmospheres. There's very little difference between the two, and for the added work you would have to do to get the Van der Waals equation and to calculate A and B, as well as the rearrangement of this equation is far more complicated. As you can see, you could potentially end up with a quadratic if you're asked to calculate the volume. So in this case, we're using the ideal gas law, as it is easier to use and accurate enough that we don't need to use the Van der Waals. Alright, 40 grams of helium is added to the container. The pressure and temperature will remain the same, and we're going to calculate the vapor pressure of helium. So the pressure of the system, as calculated from before, will be 42.2. We're using the ideal gas equation, as that is a lot easier and not better calculations, just those easier numbers. Now the number of moles of nitrogen will be 12.64 as calculated previously. The number of moles of helium that will be added is 10. Moles of helium is added to the system. Now if you add those two together to get the total number of moles that now the system after here has been added, you get 22.64. Now with that, if you find the mole fraction of each of these gases, you do 10 divided by 22.64, should be around 0.44 there. We really want to look at helium because nitrogen, we're not asked to calculate that. You take the 0.44, you multiply it by the total pressure of the system, which is 42.2, and you come out at 18.65 atmospheric pressures helium that has been added to the system. Cut. Alright, now finally we need to sketch a Maxwell-Boltzmann distribution of neon and helium in the system, and also calculate the root mean square of neon and helium. And the root mean square is an equation which is U S, is actually just square root of 3 times by R, which is a constant, times by T, which is temperature, divided by the molar mass, whatever it is you're looking at. And now for neon, the root mean square, the square root of 3 multiplied by 8.314. Now using 8.314, as we're looking at energy, so we look at joules per Kelvin per mole, and times that by temperature, which in this case for this system will be 122. Divide that by the molar mass, which would be 20.179, divided by 1,000. And you get the units to balance out. And the root mean square of neon would be 388 meters per second. Now, of helium, the same thing up here, would be square root of 3 times by 8.34 times 122 all over 4 divided by 1,000, which equates to 872 meters per second. Now, with these values, we can then quite easily plot the Maxwell-Boltzmann distribution, which would be akin to probability, and the molecules having the speed, and the actual speed of these molecules. Gas, obviously it's 0 would be 0. Only a brief sketch, but as you can see, that this first higher peak and taller peak would be neon, as it has lower energy, but be squished together, so the probability of these molecules having this 388 meters per second kinetic speed is more likely. However, helium has a higher root mean square, so even though it has a higher root mean square, it will be spread out a bit more between all these molecules. Henceforth, here be around 8, 7, 2, about 3, 8, 8. Go. That'll be alright. Alright then. So what are some of the uses of the ideal gas equation, or ideal gas law? Well, this is it here. As you can see that aside from being able to rearrange it to make whatever you want the value of it, or subject, you can see that you've also got a number of moles. And with that, it can be used in stoichiometric problems which involve gases, which is rather useful, especially in equations and looking at equilibrium. And then with that as well, is that you have standard temperature and pressure. And with this, you can set it as a benchmark to look at gases. And with this benchmark, you can compare the properties of gases as well as calculate the density using volume and times the number of moles by its molecular mass. And that's pretty much some of the applications of the ideal gas law. This has been my TED talk.